Good afternoon or morning, everyone, and welcome to the second installment of our RadarScope Lunch and Learn. My name is Marcus, and I'll be your moderator for today. If you have any questions during today's presentation, you can write your question in the chat window. And also be sure if you tweet or post on Facebook about RadarScope to use our hashtag #RSWX16. I'd like to introduce Daphne Thompson, who leads up our meteorological outreach, and Daphne will be presenting today's RadarScope topic. And at the end of today's presentation, I'm going to tell you a little bit about Skywise, Weather as a Service. Remember, RadarScope is one of the top 3 mobile weather apps available on the mobile market today, with more than 300,000 users globally. Another fact about WDT is that we hold and license 58 patents related to weather detection technologies. But what you don't know is that many sources you currently go to for your weather news and information get some or all of its data from WDT. I'd like to now turn this over to Daphne. She holds a degree in meteorology from the University of Oklahoma and brings to WDT a deep pool of knowledge. Her previous experience includes working at the National Weather Center, the Norman Emergency Management Office, and the National Weather Service. Daphne serves in a meteorological outreach capacity for WDT. And with that, Daphne, you now have the audience.
Welcome, everyone. Last week, we discussed some basics on weather radars. We learned that the covering is called a radome and that the radar is contained within it. We also talked about how data can vary depending on the distance it is from the radar. Storms farther away can end up having the beam height thousands of feet up in the atmosphere, while storms closer to the radar give a more accurate representation of the storm. Here we have a storm near Frederick that is far away from the radar near Oklahoma City. The image is very blocky. And here we see the same storm with a radar much closer. The image is much clearer and more accurate. Today, we are focusing on reflectivity data from RadarScope. We will be covering the following topics in this webinar. First off, color tables and rainfall. Then we'll have the difference between hail, rain, and other things. And finally, I'll talk about the difference between base reflectivity and Superrez reflectivity. So first off is color tables and rainfall. Whether you want to check out the rain or wanting to view a supercell thunderstorm producing a hook echo, reflectivity radar can help. Reflectivity is a radar product that displays the amount of power returned to the radar after it is reflected off particles in the atmosphere. It is measured in decibels, which is abbreviated as dBz. So what does that really mean? Well, when the radar sends out a beam, some of the energy from the beam is reflected back to the radar. Small objects, like tiny raindrops and bugs, will send back a smaller amount of energy. Larger objects, like big hail, will send back more energy. The energy that returns is then assigned certain colors. Here is a very colorful reflectivity image from a severe thunderstorm in South Texas. Yellow signifies moderate rain. The orange area will be experiencing heavy rain. Areas in red have very heavy rain and probably some small hail, while pink areas have intense rain and possibly large hail. It is important to note that these values usually change when viewing a hurricane. So the radar sends out a signal or energy while it rotates and scans the atmosphere. Then it listens for the energy reflected back. It also elevates the beam during each scan. Each elevation change is referred to as a tilt. RadarScope allows us to view 4 different tilts of radar data. Here we have a severe thunderstorm west of Austin. Let's focus on the heaviest rain or hail in the warning. I will keep the distance from the radar exactly the same and only change the tilt level. One thing to notice is that not all the tilts come in at the same time, but all of these images were captured within a few minutes of each other. Tilt 1 shows us the radar at this distance is 6,300 feet high. Tilt 2 is at 8,400 feet high. Tilt 3 we find at 11,100 feet up. And Tilt 4 has the radar gathering data at 14,600 feet. This can be useful in finding out if a storm is only intense in lower scans or if that intensity is found throughout the storm. As the radar sends out its signal, the beam travels out and returns energy along the way until it gets to its max distance. If a beam is going through rain, it bounces off the raindrops and leaves less energy to travel to more distant storms. So sometimes a storm further away may appear weaker than it really is because another storm closer to the radar has not allowed more energy to get to it. You've probably noticed that storms far away from the radar and at higher tilts can give a blocky appearance. These blocks are more formally known as pixels or gates. It's a bit reminiscent of an 8-bit video game. Since the radar spreads with distance, the pixel size change as the radar beam gets further away from the radar. You can see the pixels along the beam here. This is called a radial. It's like the spokes on a bicycle wheel. There are multiple radials extending from the radar in this rainstorm. By the way, these pixels aren't flat. They are three-dimensional boxes. If I measure the size of a pixel at the max distance from the radar, you can see that, in this case, it is about 2 miles wide. Now let's look closer to the radar and measure the same distance. Now about 40 pixels fit in the same width. Sometimes people will smooth the radar data so that you can't see the individual pixels. Although it may look pretty, it is not accurate, especially when they overlay it on a map and try to make you believe they can see exactly what is going on at an intersection in your town. In reality, the radar pixel may be the size of your entire neighborhood. Let's return for a moment to our radar sending out a signal and receiving the reflected energy. Remember, the data returning will be displayed as pixels and colored according to the decibel measurement. The three-dimensional pixels can contain raindrops, hail, bugs, smoke, and other non-weather items. Here we have two cubes that represent pixels. The one on the left has large raindrops, and the one on the right has lots and lots of small raindrops. When the radar beam bounces off these drops, it will return the same decibel value. That's because a regular weather radar is not able to differentiate between the two. While the reflectivity values are the same, the rainfall rates will differ substantially. Let's move on to hail or rain or something else. Have you ever heard the TV meteorologist say that there was going to be nickel-sized hail where you live, and instead you ended up with giant raindrops? Just as the radar is not able to tell the difference between large raindrops and lots of tiny raindrops, it can also have problems telling the difference between large raindrops and hail. So while the reflectivity values may be the same, what you get when the storm arrives may be different. However, sometimes radar images can show that hail is in the storm. These are called hail spikes or three-body scatter spikes. If you ever see this, there is a good chance that there is very large hail within the storms. This is a false signal or echo. There actually isn't any rain occurring there. What happens is that the beam leaves the radar, it hits the large hail and bounces to the wet ground. Then it bounces back to the hail before finally returning to the radar. This confuses the radar, making it believe that there is more rain beyond the area of hail. When you view the radar data afterwards, the hail spike appears. There are many things we can see on reflectivity data. On the left is a thin line front moving to the southeast. Many times these will have bugs that get caught in the wind change and the radar is reflecting off of them instead of rain. The same thing happens in the outflow of thunderstorms seen in the middle image. The picture on the right is displaying a squall line with a trailing rain curtain. Let's look at some more RadarScope reflectivity images. Here on the left, we see some rain bands on the East Coast associated with Hurricane Sandy. The middle image is that of a blizzard in the Denver area. What do you think we are looking at on the right? If you guessed some sort of precipitation, you'd be wrong. This was from a clear summer day. What you are actually viewing is a horde of grasshoppers. Park rangers reported this swarm. Otherwise, it would have been very hard to know what was going on. Sometimes it's hard to know what you're looking at without additional information. Here, the image on the left with the bright pink areas isn't heavy rain. Those are wind farms. Tall buildings and towers near a radar can block the beam and give false signals. Meteorologists aren't the only people who look at radar. Ornithologists have been known to view radar to keep track of birds and bats. We see bats leaving their caves in the center image. You can also use radar to see smoke when large fires happen, as seen on the right. I'm going to show you a few videos now. If you have a weak connection, they may not show properly. Remember, this webinar is being recorded so that you can go back and view it again later. So what I really enjoy is viewing loops of interesting storm features. On the left, check out the curlicue that goes through Frederick. Let's watch that again. The middle video shows us a feature called a bookend vortex. The top of the squall line begins to rotate inwards. We'll take another look at that. And of course, loops of reflectivity are also great for picking out hook echoes in supercells. This caused a damaging tornado near Tulsa. My final section is about base reflectivity and Superrez reflectivity. What is the difference between base reflectivity and Superrez reflectivity? Let's look at the same storm taken at the same time. Both images use 256 colors to display the data. On the left is base reflectivity, and on the right is Superrez reflectivity. If you recall from earlier, the pixels along a beam are called radials. In the base reflectivity, the radial is using wider pixels. But Superrez shows the full resolution of the WSR88D. You can see the pixels are about half the size as on base reflectivity, so the image ends up being higher resolution and able to show more atmospheric details. If you want the most detailed image on RadarScope, make sure you are selecting the Superrez reflectivity option. Let's review some of what we learned today. Reflectivity displays the amount of power returned when the beam reflects off particles in the atmosphere, such as raindrops. As a radar rotates and elevates, this gives us various tilts. RadarScope lets you look at data. When looking at storms, the line of pixels is called a radial. Pixels get wider as they get further away from the radar. Be careful of places showing very smooth data because it is giving you a false view of the storm. The Superrez reflectivity data found in RadarScope is true high-resolution radar data and is not smooth. Finally, reflectivity data is a great way of viewing storms, but it also shows non-weather phenomena like bugs, bats, and smoke. Next week, we will be talking about velocity data. Right now, though, I'm going to turn this presentation back over to Marcus.
Thank you, Daphne, for sharing your knowledge and expertise with us again today. But we're not done just yet. I'm really excited to tell you about Skywise, a premium weather data for developers that might be interested in including premium data into their own applications. So as I said, Skywise is premium weather content and analytics that you can utilize for any size project. With Skywise, you can access an enormous amount of value-added weather data and analytics never before available outside of WDT. Skywise will empower web, mobile, GIS, software as a service, and common operating picture developers, as well as data scientists, the ability to tap into a substantial catalog of weather analytics and information. Excuse me. The Skywise Current and Forecast API provides access to current weather conditions for any location across the world, as well as hourly and daily forecasts for the next 10 days, utilizing WDT's proprietary weather prediction solutions for use in any application. Add WDT's conditions and forecast data to your mobile application, and WDT's feeds can drop right into any iOS or Android implementation. And because it's a library, it's easily added to your apps and offers over 24,000 current weather observations. This feed is additive, meaning you can bring additional content from other sources if you would like to combine sources within your apps that you utilize with our stuff. Now, WDT provides a turnkey interactive weather map solution for mobile app developers. Skywise tiles drop right into any MapKit implementation with ease. And again, because it's a library, it's easy to add to your apps, and there's no source code to be concerned with. Skywise tiles are also additive, meaning you can bring additional map layers from other sources that you can combine with your own. We can serve you all types of different data sets: marine and wave, aviation, radar and satellite, point and contour, along with forecast models. We can also provide you with lightning data. With our Skywise platform, you'll have access to the most complete lightning data available. WDT Skywise is an authorized distributor of both Worldwide Lightning Location Network and Earth Network's Total Lightning Network data. The power of these global systems are immense, and immediate value can be added to your project. We make it really easy to integrate both LDM and HTTP delivery types of this data. Now let's take a look at a couple of popular apps available on the mobile marketplace that uses WDT Skywise data. First is the NOAA Weather Radar by Apollon. NOAA Weather Radar is a powerful yet easy to use weather station right on your device. Simple and stylish, but technologically advanced, OneWeather offers an alternative to cookie cutter type apps. A full suite of accurate, up-to-the-minute weather tools can keep you informed. And again, utilizing WDT's data. On the ground and in the air, pilots worldwide depend on ForeFlight Mobile for flight planning, charts, weather, airport information, document management, synthetic vision, and much, much more. And in the aviation environments, pilots using ForeFlight depend on WDT for their flight planning and en route weather. Scripps Storm Shield, which is distributed across their network areas, utilize our data so their customers can get severe weather alerts for exact locations, again, on their iPhone or Android device. All of the weather data that you would ever need, you can get directly from WDT. Don't get your weather data feed from a bargain basement or even free sources. Have guaranteed uptime and extremely fast delivery. As you've just seen, many sources of weather data that you could be receiving today might just come from WDT. So get in touch with me by calling the number on the screen or send me an email and learn more about what types of data we can provide you for your own groundbreaking applications. And that concludes today's webinar presentation. I'd like to thank you all for attending and have a great rest of your day.